Colour and light, but it's only part of the show. Visible light, the rainbow in the middle, is just part of a whole spectrum of radiation. It stretches from gamma rays at one end to radio waves at the other. That tiny band of visible light is the only radiation we see. All radiation is invisible. We see light because it reflects off particles in the atmosphere. The sun in ordinary visible light. Just a fraction of its radiation, but there are clues. Our bodies sense infrared as heat and ultraviolet as suntan. Like us, optical telescopes see only visible light. They miss the big picture. To catch the full spectrum of the universe, we need a different astronomy. It's awful. The orchestra's playing properly, but we are hearing just a small range of notes. That's how it is with the sky. Visible light is a note or two in the spectrum. We need the whole range, all radiation, to hear the full cosmic orchestra. Radio waves are the longest in the radiation spectrum. We catch them in dishes and bingo, we have pictures. A quasar, the core of a distant galaxy. An image in both visible light and radio. Take out the visible and radio reveals what it brings to the picture, especially the jet. An optical picture of the galaxy Centaurus A. Radio shows it's in turmoil, the aftermath of a galactic collision. A pulsar, a tiny super-dense star spinning 30 times a second. With radio, we see its powerful radiation beams. Along the spectrum, from radio to infrared. Infrared can be gathered only in the driest places. Water vapor absorbs it. Arid mountaintops, or the wastes of Antarctica, are good. Water at the South Pole is well and truly frozen. To astronomers, infrared is important. It picks out warm cosmic dust. But like ultraviolet and the longest radio waves, relatively little penetrates our atmosphere. By and large, only visible light gets through. Most invisible radiation is absorbed by our atmospheric shield. To overcome the problem, detectors operate in Earth orbit. This is ISO, the Infrared Space Observatory. ISO must keep cool or be blinded by its own emissions. Anything hot radiates infrared. Veins of circulating liquid helium absorb heat and vent it from the craft. ISO is the coolest laboratory in the universe, minus 270 degrees Celsius. But infrared pictures are hot. Here in the constellation of Orion, infrared unveils vast clouds of gas and dust, a birthplace of stars. In ordinary light, the Large Magellanic Cloud, a galaxy very close to our own. In infrared, it displays great wafts of dust, where stars are born. The Andromeda Galaxy in ordinary light, and here in changing wavelengths of infrared. By highlighting clouds of starbirth, infrared reveals Andromeda's spiral structure. Within our own galaxy, ISO gathers radiation from clouds between stars. Its long-wave spectrometer specializes in the job, imaging nebulae in the pangs of stellar birth. Still in infrared, but closer to home, ISO tracks a comet, its trail like condensation from a jet plane. In ordinary light, a comet's heart is obscured. But infrared gets through. and to the shells of dust that surround it. The composition of a comet, a fingerprint in infrared. In 1997, ISO divines water on comet Hale-Bopp. And when ISO peers toward our galactic center, there's water there too, in abundance, a medium for life. ISO, an eye on the invisible. By contrast, the Hubble Space Telescope is famous for the visible. But Hubble has peripheral vision too, infrared to one side, ultraviolet to the other. It's like stripping the veneer of a cosmic portrait. In ordinary light, a Hubble detail of the Orion Nebula. Pierce the dust with infrared, and Hubble uncovers cocoons of young stars. Again, in ordinary light, this Hubble picture hints at the next stop on the spectrum. The blue halo is from hot young stars radiating ultraviolet. The Andromeda Galaxy in ordinary light. But in ultraviolet, clouds of hot gas where massive stars die young. Halley's Comet in ultraviolet. The dark blue, a cloud of hydrogen enveloping the entire comet. Time-lapse of the Sun, ultraviolet unmasking its churning surface. Shorten the wavelength to X-rays, and there are the hottest, most energetic regions, plus the corona, the searing atmosphere of the Sun. The night sky as we see it, and as it is in X-rays. The orbiting observatory ROSAT targets the hot spots of the cosmos. It discovers 60,000 sources of X-rays. Like this galaxy with its turbulent core and very possibly a black hole. No doubt about galaxy M87 at the left. The neighboring blob is confirmation. It is material jetting from a black hole, better seen in this X-ray simulation. The remnant of a supernova, X-rays from the quivering entrails of an exploded star. Another, the Crab Nebula, with its pulsar, the relic of the star that exploded. It spins like a top, flashing like a lighthouse. In X-rays, here's the pulsar switched off. And here, switched on. It happens 30 times a second. X-rays reveal the sheer energy of the pulsar. It lights up the whole nebula. From Space Shuttle, the Compton Observatory is released into orbit. It detects gamma rays, the most energetic radiation of all. Compton finds it here, shooting from a supermassive black hole, jets of gas at 100 million degrees. And Compton charts gamma ray bursters, mysterious blasts of energy. They seem to come from the farthest reaches of the cosmos. In gamma rays, a panorama of our galaxy, the Milky Way. The hot band across the center, cosmic rays colliding with interstellar gas. The Milky Way in X-rays. In infrared, showing lots of dust. In the wavelengths of radio. And in the radiation we know best, visible light. Just part of the cosmic orchestra, but nonetheless exquisite.